Hello, I'm Stacey Ross, and this is my presentation for Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to use Faraday's law to understand the relationship between magnetic flux and induced charges. For this lab, I collected observational data of a magnet falling through a conductive tube of aluminum foil, modeled the interaction between the magnet and tube computationally, and compared my computational predictions with observed data. The materials required for this lab are a smartphone, bar magnet, roll of aluminum foil that still has at least 1 centimeter remaining, and a measuring tool such as a meter stick. Before we get started on the actual experiment, let's answer the checkpoint question. Why can't we use a ferrous tube such as a steel pipe? The reason we can't use a ferrous tube such as a steel pipe is because the magnet would stick to the inside of the tube rather than falling through. Before we begin, I'm going to introduce a few concepts and equations that will be important in the understanding of this lab. First, Biot-Savart law, which describes the magnetic field due to constant electric current. Biot-Savart law states that magnetic field is equal to mu naught over 4 pi times 2 mu over r cubed. Next, we have magnetic flux, which is equal to the integral of the magnetic field dotted with the normal direction dA. Faraday's law states that induced current is equal to negative n times delta phi over delta t, where n is the number of loops. Finally, we will use Newton's second law, which states that the potential difference is equal to F net over mass times delta T. The change in position is equal to V times delta T. Before beginning the experiment, I measured the length of the aluminum foil tube. Next, I set the tube up vertically so that the bottom was uncovered. This way, I could see when the magnet reaches the bottom. I set up my smartphone to record the entire length of the tube. I dropped the magnet through the tube and used the video to determine how long it took for the magnet to fall. I repeated this procedure 5 times and calculated the average travel time for the magnet. These were the results of my 5 trials, for an average of 2.4 seconds. Here we're asked another checkpoint question. What happens to the magnet? How does this compare to a magnet falling in free space without the tube? We know from Faraday's law that an electrical current is induced through the aluminum foil. The current generates another magnetic field that opposes the magnetic field of the bar magnet and causes the bar magnet to fall slower than it would without the tube. Next, we're asked to create a computational model in GlowScript. After familiarizing myself with lecture video 43, Force on a Magnetic Dipole, I used the Lab 5 starter code to create a computational model of the magnet falling through the tube. In the starter code, the bar magnet is modeled as a point dipole, and the conductive tube is modeled as a stack of non-interacting conductive rings. First, I inserted the measurements of the tube, including length, radius, and the thickness and the magnetic moment of the bar magnet found in Lab 3. Next, I calculated the magnetic field at a point R relative to a bar magnet and the rate of change in the magnetic flux through each ring caused by the falling magnet. Using Faraday's law, I calculated the current induced in each ring by the falling magnet. I used the Biot-Savart law to calculate the force exerted on each current-carrying ring by the falling magnet. Then, using Newton's third law, I calculated the force exerted on the falling magnet by the whole tube of current-carrying rings, assuming that the tube stays fixed. I calculated the net force on the magnet, including gravity, and used Newton's second law to write position and velocity updating code to model the motion of the falling magnet. This is the simulation my computational model produced. The total fall time predicted by the model was 2.523 seconds, which is very close to the experimental average of 2.4 seconds. The number is not exact, probably due to some human error on my end when timing the fall of the magnet. Now we need to discuss some of the visualizations produced by the model. First, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. We're asked which color responds to clockwise current and which counterclockwise, and how can we know? The red current is clockwise and the blue current is counterclockwise. We know this from the right-hand rule based on the direction of the magnet. The current induced above the magnet will be clockwise and the current induced below will be counterclockwise. How does the total time in tube of my real-world system compare to that of the computational system? How might the computational system be made more accurate? The computational model was slower by 0.123 seconds. This could be due to human error when recording the travel times or exterior magnetic fields. To improve the model, we might consider the magnetic field of Earth and nearby electronics. What does the shape of the velocity versus time plot tell us about the forces acting on the bar magnet? The bar magnet reaches a constant terminal velocity, meaning the net force is zero. We're asked, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? According to Ohm's law, a lower resistivity would cause the induced current to increase in magnitude, making the tube's magnetic field larger and causing the magnet to fall slower. What if holes or slots were cut into the tube? How would this affect the ring currents in my model? The induced current would be interrupted at each slot. Therefore, the tube's magnetic force would decrease in magnitude, causing the magnet to fall faster. That's all. Thanks for watching.